Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. In my last class, I discussed the concept of image texture analysis. So what is texture? Texture means spatial distribution of gray level intensities. I discussed 4 research directions. One is texture classification, one is texture synthesis, one is texture segmentation, and one is shape from texture. A particular texture can be represented or described by 3 techniques I highlighted. One is the structural method, one is the statistical method, and one is the spectral method. In case of the structural method, I have to find a placement rule for the texels. Texel means the basic unit of a texture, that is the primitive. Texel means a group of pixels having homogeneous property. And based on this texel, I have to find the placement rule for the structural representation of a particular texture. The next one is the statistical method. So I have to extract some statistical parameters, and based on these parameters I can represent a particular texture. And finally I discussed the technique is the spectral method. In spectral method, I have to determine the Fourier transform of the image, and based on the Fourier transform of the image, I can represent a particular texture. Last class I discussed the statistical methods for texture representation. So for this I can extract some statistical parameters like mean, standard deviation, third order moment, like this I can extract, and based on this I can represent a particular texture. After this I discussed the concept of GLCM, the gray level co-occurrence matrix. So today I am going to discuss some other texture descriptors. So one is the autocorrelation function that I am going to discuss today. Another one is very important, that is the Gabor filter based texture representation. So I can extract texture features by Gabor filter, and finally I will discuss the concept of local binary pattern, LBP. So how to represent a particular texture by using LBP. So let us see the concept of the GLCM that I discussed in my last class. So you can see in my last class I discussed the concept of the GLCM. So from the input image I can determine the GLCM, that is the gray level co-occurrence matrix, and in this case I am considering 3 gray levels. So that is why the Pij will be 3 by 3 matrix. And for GLCM I have to define the displacement vector. So the displacement is 1 and 1. Suppose I can consider another example of GLCM. Suppose my input is 1 1 0 0 1 1 0 0 0 0 2 2 0 0 2 2. So this is my input image, and in this case I will be getting the 3 by 3 gray level co-occurrence matrix. So suppose my displacement is 1 0. In x direction it is 1, and in y direction it is 0. So corresponding to this D10, my array, the array is Pij. The Pij will be, you can verify this, 402, 220 and 002. So this is my array. Also, if I consider a displacement, suppose, and D01, corresponding to that displacement, my Pij will be, that is the gray level co-occurrence matrix, 420, 020, 202. That is for a displacement D01. And suppose if I consider a displacement D11, that is in the x direction it is 1 and in y direction it is 1. So corresponding to this displacement, the Pij will be 3 1 1 1 1 0 1 0 1. So you can verify this. So what is the method? So for all the displacements, so different displacements, I have to find the GLCM. That is, GLCM is computed for several values of D, and the one which maximize a statistical measure computed from Pij is finally used. So that is the concept of GLCM. And also in my last class I discussed about the normalization procedure. So we have to do the normalization of the gray level co-occurrence matrix. So in this case, in this example, if you consider this example, what I have to consider, these elements we have to divide it by 16, because 16 pairs of pixels in the image satisfy the spatial separation condition. So that is why 0 is divided by 16, 2 is divided by 16, like this I have to consider corresponding to this co-occurrence matrix. So I have to do the normalization. And from the GLCM, I can extract some features, the statistical features. The parameters are like this. The maximum probability I can determine, the moments I can determine, contrast I can determine, uniformity and the homogeneity also I can determine from the GLCM, and finally one important parameter, that is the entropy, also I can determine. After this I discussed in my last class the concept of the spectral representation of a texture. So for this you can see the texture is nothing but repetitions. So if I consider a texture, it is nothing but the repetitions of these texels. So that is the regularity in the texture. So for this what I can do, I can determine the Fourier transform of an image. So suppose Sxy is the Fourier transform of the image. So in the Fourier transform, the prominent peaks in the Fourier spectrum give the principal directions of the texture pattern. So that is the first point, that is the prominent peaks in the Fourier spectrum give the principal directions of the texture pattern, and also the location of the peaks in the frequency plane gives the fundamental spatial period of the patterns. So this is the concept of the Fourier transformation. This Sxy, that is the Fourier transformation, the 2D Fourier transform of the image, that I can represent in the polar form S r theta. I can convert to the polar coordinate. Last class I discussed about this, and I can consider this case S theta r, and another one is S r theta I can consider. The first case is, what is the first case? The theta is fixed, and in this case I want to find the behavior of the spectrum along the radial direction. So this is the theta is fixed. Theta is fixed, and I want to see the behavior of the spectrum along the radial directions. In the second case, the r is fixed, and I can see the behavior along a circle centered on the origin. So because the theta is variable here, r is fixed, that means I can see the behavior along a circle centered on the origin, that I can see. And based on this I can compute SR and the S theta I can compute. So sum all pixels in each area and sum all pixel in each area I have to consider, that SR I am determining, another one is S theta I am determining. And you can see this example corresponding to this original image, I am determining the 2D Fourier transform, that is the 2D Fourier transform I am determining. And you can see these two spectrums, one is SR, another one is S theta, corresponding to this image. And if I consider another image, the textured image, corresponding to this image, you can see the spectrum S theta. So S theta is different. If you see these two spectrum, it is quite different. So that means based on SR and S theta, I can represent different types of textures. This is about the Fourier approach for texture representations. Now next one is the autocorrelation function I can consider. So in this case, one important property of textures is the repetitive nature. Repetition is due to the placement of the texture elements. The texture element is the texels in the image. So that is a repetition due to the placement of texture elements, texels in the image. So in this case, this autocorrelation function, it is used to identify the amount of regularity of the pixels of the image, and it can be used to estimate fineness and the coarseness of the texture. That is one important point. This autocorrelation function can be used to estimate fineness and the coarseness of the texture. An autocorrelation function can be used as a measure of periodicity of texture elements. An autocorrelation function is directly related to the power spectrum of the Fourier transform. This autocorrelation function is defined like this, corresponding to the image is fxy. So this is the definition of the autocorrelation function. So fkl I am considering fk plus x l plus y, and after this we have to do the normalization. This is the f square kl. So this is the definition of the autocorrelation function. These autocorrelation functions drops off rapidly for fine textures. So I can write like this: autocorrelation function drops off rapidly for fine textures. And for regular textures, the autocorrelation function has peaks. Autocorrelation function has peaks and valleys. So that means the autocorrelation function can be used as a measure of periodicity of texture elements. And here I have shown the two cases. The autocorrelation function drops off rapidly for fine texture. So for fine texture, it drops off rapidly, and for regular textures, the autocorrelation function has peaks and valleys. And also the autocorrelation function can be used as a measure of periodicity of texture elements. Now suppose if I consider FUV is the Fourier transform, the 2D Fourier transform of the image, and FUV whole square is called the power spectrum. So the spectral features can be extracted by dividing the frequency domain into rings and wedges. So in the figure you can see I am considering some rings. You can see the rings. These are the rings. I am considering the Fourier transform. The spectral features I can extract by dividing the frequency domain into rings, or maybe the wedges. The wedges, suppose if I consider this is the wedge, I can consider. The rings are used to extract frequency information, while the wedges are used to extract orientation information of the texture pattern. So the rings, these are rings are used to extract the frequency information. And these, the wedges, I am using to extract the orientation information. The wedges are used to extract the orientation information. And after this, the energy features can be computed in each annular regions. I can compute, and it indicates the coarseness or fineness of a texture pattern. So I can determine the energy. I can determine the energy for the annular regions, and it indicates the coarseness or the fineness of a texture pattern. Also, I can determine the energy features in each wedges, and these features indicates the directionality of a texture pattern. So that means I can determine the energy features in the annular regions, and also I can determine the energy features in each wedge. And in this case you can see I am considering the power spectrum. So this is the power spectrum. In the first case, I am calculating f r1 r2 I am calculating. So in this case, what I am considering, that means all the angles I am considering, that is for the annular rings. So this ring I am considering, this is the annular rings. So the angle is from 0 to twice pi I am considering. So this angle is from 0 to twice pi, that I am considering. And but radius is from r1 to r2 I am considering. That annular rings I am considering, and I am determining the fissure. The fissure is f r1 r2. In the second case, what I am considering, f theta 1 theta 2, and in this case I am considering the radial distance from 0 to infinity. 0 to infinity, that distance I am considering, the radius. But angle I am considering from theta 1, the angle is suppose this theta 1 to this direction is suppose theta 2. So that is this angle theta 1 and theta 2 I am considering, and that means I am considering this wedge. This is I am considering, and corresponding to this I am determining the fissure. The fissure is f theta 1 theta 2 from the power spectrum. So this FUV square is the power spectrum. So from the power spectrum I am determining these two fissures. One is f r1 r2 and another one is f theta 1 theta 2. So that means we can see the behavior of the texture, the fineness or the coarseness, and also we can see the direction of a particular texture pattern, that we can see from these two fissures. One is f r1 r2, another one is f theta 1 theta 2. So this is about the autocorrelation function for representation of a particular texture. The next one is very important, and that is the Gabor filter based texture representation. That is, I can extract texture fissures by using a Gabor filter. So what is a Gabor filter? You can see a 2D Gabor function consists of a sinusoidal plane wave of a certain frequency and orientation modulated by a Gaussian envelope. That means I am considering a 2D sinusoidal function. So here you see s omega theta xy, that is the sinusoidal plane wave, and I am considering the frequency is omega and orientation is theta, and that is modulated by a Gaussian function. The Gaussian function is z theta xy, that is the Gaussian function. And if I consider these two functions, one is the sinusoidal function, another one is the Gaussian function, then I will be getting the Gabor function, the 2D Gabor function I am getting. And in this case you can see the z theta xy, that is the Gaussian function, the 2D Gaussian function, and in this case you can see the sigma x square, that is the variance along the x direction, and the sigma y square, that is the variance along the y directions. This actually represents the spread of the Gaussian function, and in this case s omega theta, that is the sinusoidal plane wave, you can see. So it has two components, one is the imaginary part, another one is the real part. Here I am considering the imaginary is I, you can see. So it's a complex function, and I am considering a sinusoidal plane wave of a certain frequency. The frequency is omega and the orientation is theta. This sinusoidal function is modulated by the Gaussian. The 2D Gaussian function is used to control the spatial spread of the Gabor filter. The variance parameters of the Gaussian determines the spread along the x direction and the y directions, and also we have the orientation parameters. So in general for the Gaussian filter, the sigma x is equal to sigma y is equal to sigma. That means that is variance along the x direction is equal to variance along the y direction is equal to sigma. It is a constant. In this case, the rotation parameter theta does not control the spread, as the spread will be circular if variances are equal. In this case I am considering the sigma x is equal to sigma y is equal to sigma. That means the variance along the x direction is equal to variance along the y direction, and corresponding to this case the rotation parameter theta does not control the spread, as the spread will be circular if the variances are equal. So, this is the definition of the Gabor filter. That means, we are considering a sinusoidal plane wave of a certain frequency and orientation modulated by a Gaussian envelope. The same thing I am showing here in this slide also. I am defining the Gabor function, the 2D Gabor function, and I am considering the sinusoidal function and also the Gaussian function. So, here you can see the z theta xy, that is the Gaussian function, the 2D Gaussian function, s omega theta. So, I am considering the parameters, the frequency parameter is omega, orientation parameter is theta, that is the s omega theta xy is the 2D sinusoid function, the sinusoidal function. Xy corresponds to a spatial location of an image. So, a spatial location of the image is considered, and in this location the Gabor filter is centered. The omega corresponds to the frequency parameter of the 2D sinusoid, and theta, already I have mentioned, the theta is the orientation parameters. And we have considered the variance along the x direction and the variance along the y directions. If this sigma x and sigma y is equal, then in this case the rotation parameters does not control the spread, as the spread will be circular if the variances are equal. The two sinusoidal components of the Gabor filters are generated by a 2D complex sinusoid. The local spatial frequency content of the image intensity variation, that is the texture in an image, can be extracted by applying these two sinusoids. And in this case you can see there are real and the imaginary components of the complex sinusoid. The two components are phase shifted by pi by 2. So, if you see the previous slide, you can see the sinusoid function, that is a complex number, and I have two components, one is the cos theta, another one is the sin theta. The phase difference between this is pi by 2, and in this case the Gaussian and the sinusoid function are multiplied to get the complex Gabor filter. So, here you see I am considering the real part of the sinusoidal function. So, r is the real, and I am considering the z theta xy, that is the Gaussian function, the 2D Gaussian function, that is the real part of the sinusoidal function is modulated by the Gaussian, and I am considering the real part of the Gabor filter. The second one is I am considering the imaginary part of the sinusoidal function, and this is modulated by the Gaussian, and I am getting the imaginary part of the Gabor function. The real and the imaginary part of the Gabor filter are separately applied to a particular location. The location is suppose x and y of an image fxy to extract Gabor features. So, here you see what I am doing. I am considering the image is fxy, that is convolved with the real part of the Gabor filter. So, this is the real part of the Gabor filter, and also you can see the next part, the second part. This is the image is fxy, that is convolved with the imaginary part of the Gabor function, and from this the real part and the imaginary part I can determine the Gabor coefficients, the Gabor features I can determine. So, c psi xy, that is nothing but the Gabor features. So, corresponding to a particular texture I can determine the Gabor features. So, the parameters are omega and the theta. Omega is the frequency and theta is the orientation. Also another parameters, the sigma x and the sigma y. So, I will be getting the Gabor features for different orientations. So, you can see how we can extract the Gabor features by considering this Gabor filter. So, I have to consider the real part of the Gabor function. So, for this I am considering the real part of the sinusoidal function, and also I have to consider the imaginary part of the Gabor function. For this I am considering the imaginary part of the sinusoidal function, and already I have mentioned what are the parameters. The parameters are variance along the x direction, variance along the y direction, the orientation parameter theta, and I can consider the frequency parameter omega. So, in this case I have shown a typical Gaussian filter with sigma is equal to 30, and in this case I am considering the sigma x is equal to sigma y is equal to suppose sigma. And another case you can see a typical Gabor filter with sigma is equal to 30 and omega is equal to 3.14 and the orientation is 45 degree that I am considering. And here I have shown the 2D Gabor filter. This is the expression for the 2D Gabor filter, and sigma is the spatial spread, omega is the frequency and theta is the orientation parameter. And in this case you can see use a bank of Gabor filters at multiple scales and orientations to obtain filtered image. Gabor filters with different combinations of spatial width, frequency omega and orientation theta. So you can see all this example 1, 2, 3, 4. So for this what I am considering the Gabor filters with different combinations of spatial width and frequency omega and the orientation also I am considering, that is the theta. So this is about the Gabor filter. So by using the Gabor filter we can extract texture features. The another important technique is MPEG-7 homogeneous texture descriptors, that is called HTD, the homogeneous texture descriptors. This HTD describes directionality and the coarseness and the regularity of a texture pattern. So what it describes? The first one is the direction of a particular texture, the coarseness and the regularity of a texture pattern. It characterizes a particular texture. So for this what I have to consider? For this the mean energy and the energy deviation from a set of frequency channels are considered. So I am repeating this. So for HTD, the homogeneous texture descriptors, the mean energy and the energy deviation from a set of frequency channels are considered, and 2D frequency plane is partitioned into 30 frequency channels. So for this we have to consider 30 frequency channels. So for this what we have to consider? The mean energy we have to compute and its deviation are computed in each of these 30 frequency channels in frequency domain. So here I have shown the pictorial representation of the HTD, the homogeneous texture descriptors, and you can see we have considered 30 channels, the frequency channels we have considered. So here what is HTD? So here you can see HTD is the first component is FDC. So what is FDC and what is FSD? The FDC and FSD are the mean and the standard deviation of the image. That is the definition of FDC and FSD, the mean and the standard deviation of the image respectively. And I am considering E1, E2, E3, E up to E30 because we have 30 frequency channels, and also we are considering the deviation. Deviation is D1, D2 up to D30 for 30 channels. So in this case the EI and DI are non-linearly scale and quantize mean energy and energy deviations of the corresponding ith channel. So that means EI corresponds to the mean energy and DI corresponds to energy deviation of a particular channel. And also the individual channels are modeled by using Gabor functions. Okay. So suppose let us consider a channel indexed by SR. So what is S here? S is the radial index, and R is the angular index. So what I have to consider? The individual channels are modeled by using Gabor functions. So I have 30 channels and the individual channels are modeled by using Gabor functions, and I am considering the channel index by S, R. S means the radial index and R means the angular index. So SR channel is modeled in the frequency domain like this. So this GSR omega theta is nothing but I am considering two exponential functions, you can see, and P omega theta that I am considering. So on the basis of the frequency layout and the Gabor functions, the energy EI of the ith Fisher channel is defined as the log scale sum of the square of the Gabor filtered Fourier transform coefficients of an image. So that means what is EI? The EI is computed like this, and you can see what is PI. The PI, it is determined from this expression. That is the definition of PI. So this is the PI. So what is P omega theta in this expression? If you see all this expression, what is the P omega theta? P omega theta is the Fourier transform of an image represented in the polar frequency domain. That is, P omega theta is equal to F omega cos theta omega sin theta. And in this case, FUV is the Fourier transform to the Fourier transform of the image in the Cartesian coordinate system that I am considering. And also I need to determine the energy deviation I have to determine. In my last slide I have determined the mean energy. Now I have to determine the energy deviation, that is the DI for a particular channel. That is defined as the log scale standard deviation of the square of the Gabor filtered Fourier transform coefficients of an image. So you can see I can compute DI by using this expression. And what is QI? The QI is obtained from this. This concept you can read from some papers on MPEG 7 homogeneous texture descriptors. So that is by HTD I can represent a particular texture. That is nothing but the texture descriptors. And finally I want to discuss another descriptors for texture, that is LBP, the local binary pattern. So LBP is a well known texture descriptors that is widely used in many computer vision applications. So for many computer vision applications, even the face recognition, facial expression recognition, other many applications, the LBP is used. LBP is computationally simple and easy to apply, and also it is a non-parametric descriptors. One important point is it can handle the monotonic illumination variation. That is one important point. So it can handle the monotonic illumination variations. So how to compute the LBP? So corresponding to this image you can see here, that is I am considering the basic local binary pattern, because LBP has many variants, but in this case I am considering only the basic LBP. So in basic LBP, each pixel of an image is compared with their 8 neighborhood pixels of a 3 by 3 block. So here you can see in this image I am considering a 3 by 3 block, and you can see the neighborhood of the pixel is 42, the center pixel is 42, and the neighborhood pixels are 202, 12, 24, 0, 42, 64, 33 and 81. That means we have 8 neighborhood. So that neighborhood I can write like this, IN, that is the neighborhood, and in this case n is equal to 1, 2, so I have 8 neighborhood pixels. Corresponding to the center pixel, the center pixel is suppose IC, that is the center pixel. And after this what I have to do? I have to determine the LBP. So how to determine the LBP? So for this, if IN, that is the neighborhood pixel, is greater than equal to the center pixel, the IC is the center pixel, this is the center pixel, and IN is the neighborhood pixel, this is the neighborhood pixel. Neighborhood pixels. And if IN is greater than IC, then in this case IN will be equal to 1, else IN is equal to 0. So this I am considering. So based on this you can see the 42 is compared with 202. Since 202 is greater than 42, so corresponding to this I will be getting 1 here, this is 1. After this the 12 is compared with 42, the 12 is less than 42, so that is why I am considering it 0. Next I am comparing 24 with 42, the 24 is less than 42, so that is why I am considered it as 0. And like this I am getting these numbers, all these numbers I am getting. So what will be the my number, binary number? 10001101. That means I have to do the binarization So binarization is done by concatenating this IN from the left top corner. So what is the left top corner? This is the left top corner. Left top corner in the clockwise direction. So clockwise direction is this is the clockwise direction I am considering. This is the clockwise direction. So that means I am repeating this. The binarization is done by concatenating this IN from the left top corner in the clockwise direction. So corresponding to this, my binary number will be 1 0 0 0. If you see this example, 1 1 0 1. That is the case. And subsequently, the corresponding decimal equivalent value I have to determine. So corresponding to this, what will be the decimal equivalent value? The decimal equivalent value will be 141. That 141 will be assigned to the center pixel. The center pixel is, this is the center pixel. So this 141 will be assigned to the center pixel IC, which is known as the LBP code. And this step is repeated for all the pixels of the image. So for all the pixels of the image, I have to repeat this step. And finally, the corresponding histogram of the LBP codes is considered as a local texture feature of the original image. So what finally I have to do? Finally, the corresponding histogram of the LBP codes we have to consider, and the local texture features of the original image I can determine. So here you see, corresponding to the center pixel, I am getting the LBP code. The LBP code is 141. So this is the LBP code for the center pixel. So for all the pixels of the image, I have to do this. And finally, the corresponding histogram of the LBP codes we have to consider, and that is considered as the local texture features of the original image. So I have to determine the histogram of the LBP codes. The LBP PR corresponding to the center pixel I can determine, and that will be the binary number, and this binary number I can convert into the decimal number. And what about this function? The function is fx. The fx will be 1 if x is greater than equal to 0, otherwise it will be 0 if x is less than 0. That means I am doing this case, that is I am comparing the center pixel with the neighborhood pixel, and based on this I am getting the value of fx, and from the fx I am getting the binary numbers, and binary numbers I am converting into equivalent decimal representation, and that is nothing but the LBP code. And there are several variants of the LBP. This is the basic LBP. So like this, I can give some example. One example is the extended LBP. Another LBP is the uniform LBP, that is very popular. Uniform LBP is very popular. So you can see all this concept from the research papers. So what is extended LBP? What is uniform LBP? But the basic concept of the local binary pattern is this. So here also I have shown one example of the local binary pattern corresponding to this image. You can see I am following the same procedure, just comparing the center pixel with the neighborhood pixels. Just I am doing the comparisons like this, and based on this I am getting the binary code. The binary code will be 1111 1100, and the decimal equivalent will be 252. That is the LBP code. And finally, there is another technique. I am not going in details about this local derivative pattern, that is called the LDP, the local derivative pattern. So this is also very popular. If you want to see this concept, you can see this paper, the research paper, that is the local derivative pattern versus local binary pattern. So in case of the LBP actually encodes the binary result of the first order derivative among local neighbors by using a simple threshold function. LBP is incapable of describing more detailed information, so that is why we consider the LDP. That means LDP considered n-1/8 order derivative direction variations based on binary coding functions. And LDP encodes the high order derivative. That is one also important point. In LDP we consider high order derivative information which contains more detailed discriminative features that the first order LBP cannot obtain from an image, because in case of the LBP we considered the first order derivative, and also we considered a simple threshold function, because I am comparing the center pixel with the neighborhood pixels, and for this I am considering a threshold function. But in case of the LDP we are considering the high order derivative we are considering, and many directions I am considering, the directions like 0 degree, 45 degree, like this different directions I am considering, and LDP encodes the high order derivative information, and that is why it contains more detailed discriminative features in the LDP as compared to LBP. So, for more details you can see this paper on LDP, the local derivative pattern. So, in this class I discussed some other texture features like autocorrelation function I have discussed, and after this one important representation, that is the Gabor filter I have considered. So, how to extract the texture features by Gabor filter, that concept also I have discussed. This is very important, and finally I discussed the concept of LBP, the local binary pattern. So, this is about the texture analysis. Let me stop here today. Thank you.